Tire cord and textile industry with looms and dipping plant. AIML, 5-fold architecture, model architect. Pradeep K. Suri. Author, researcher, and AI-DNN architect. Explanation. Left side. A textile factory with multiple spinning machines. The machines are spinning thin threads of yarn. The yarn is being wound onto bobbins. Right side. A cross-section of a tire, showing its layers. The layers include the tread, rubber, steel belts, and textile cords. Connection. The image highlights the connection between the textile industry and the tire industry. The textile industry produces the yarn that is used to create the textile cords in tires. These cords provide strength and reinforcement to the tire. Tire cord looms. Let's explore the world of tire cord looms, using the provided image as a reference. Understanding tire cord looms. The image showcases a tire cord loom, a specialized weaving machine designed to produce the high-strength fabric used in the construction of tire cords. These cords are the critical reinforcement within a tire, providing the necessary strength and durability to withstand the stresses of driving. Key components and process. While the image provides a glimpse of the machine, let's break down the essential components and the overall process. 1. Warp beams. These large beams hold the lengthwise yarns, warp, that form the base of the fabric. 2. Heels and sheds. Heels are frames with eyes that lift and lower warp yarns to create openings, sheds, for the weft, cotton, yarns to pass through. 3. Weft insertion. The weft yarns, typically made of high-density fibers like nylon, polyester, or cotton, are interlaced through the sheds to create the fabric structure. 4. Reed. The reed, a comb-like structure, separates the warp yarns and compacts the weft. 5. Roller assembly. The newly woven fabric is rolled onto a roller for further processing. The tire cord loom in action. The image likely depicts a loom in operation. The control panel might be used to adjust weaving parameters, and sensors could monitor tension and other critical factors. In conclusion, tire cord looms are specialized machines that play a vital role in tire manufacturing. The image gives us a glimpse into this process, highlighting the key components and the overall production flow. To gain a comprehensive understanding, exploring the internal mechanisms and the specific materials used would be beneficial. Explanation. The image shows a tire cord dipping machine in operation. This machine is used to coat textile cords with rubber, a crucial process in tire manufacturing. Key components visible in the image. Metal rollers. These are responsible for guiding and controlling the movement of the textile cord through the dipping process. Textile cord, the copper-colored material being processed. It is a newly dipped cord, as it appears wet or coated. Dipping tank. Though not fully visible, the machine likely has a dipping tank filled with rubber compound where the textile cord is submerged for coating. Overall, the image provides a glimpse into the initial stages of tire cord production, where the textile base material is prepared for integration into tire construction. For the above tire cord and textile plant, tire cord looms. With dipping plant AIML model. From a management perspective, the provided AIML model demonstrates several key elements of data analysis and predictive modeling. Here's a breakdown of the AIML model and its relevance to management. 1. WIP data. Purpose. The program gets data from work in progress, WIP, in the tire cord and textile industry. Importance. Getting realistic data helps in simulating real-world scenarios and testing the performance of predictive models. 2. Forecasting. Forecast data creation. The program generates forecast data for future years, 2024 and 2025. Importance. Forecasting is crucial for planning and budgeting. This allows managers to anticipate future needs, allocate resources efficiently, and make informed strategic decisions. 3. Machine learning model. Random forest model. The program uses a random forest regressor to predict the total value of WIP based on features like denier, quantity, and unit price. Cross-validation. It employs 5-fold cross-validation to evaluate model performance. Importance. Machine learning models provide predictive insights that can drive decision-making processes. Cross-validation ensures the model's reliability and accuracy, reducing the risk of poor predictions. For model evaluation. Metrics: the program calculates performance metrics like RMSE, root mean squared error, and R-squared for both training and testing data sets. Importance: evaluating model performance helps in understanding its effectiveness. For managers, these metrics indicate how well the model can predict future outcomes, guiding confidence in the model's predictions. 5. Visualization. Heat maps: the program creates interactive heat maps to visualize the correlations between different features. Importance: visualization aids in understanding complex data relationships and patterns. For managers, heat maps can highlight key factors affecting WIP values and guide decision-making. 6. Performance tracking. Processing time: the program measures the time taken to execute the various operations. Importance: tracking processing time helps assess the efficiency of data handling and modeling processes, which is crucial for optimizing performance and resource utilization. Summary for management. 1. Data simulation: the program simulates realistic WIP data, allowing for effective testing and forecasting. 2. Forecasting capabilities: by generating forecast data for future years, the program supports strategic planning and resource allocation. 3. Predictive modeling: using machine learning models like random forest helps in predicting WIP values, which can influence decision-making and strategic initiatives. 4. Model validation: cross-validation and performance metrics ensure the reliability and accuracy of predictions, providing confidence in the model's results. 5. Data visualization: interactive heat maps help visualize complex data relationships, making it easier to identify trends and make informed decisions. 6. Efficiency monitoring: measuring processing time helps in optimizing the program and ensuring efficient data handling. Overall, this mentor program provides valuable insights and tools for managers to make data-driven decisions, improve forecasting accuracy, and optimize operational processes. Explanation in detail: AI/ML engine RMS and R-squared. Average cross-validation RMSE, 7336.86. Average cross-validation R-squared, 0.96. Training RMSE, 2488.84. Testing RMSE, 2019.47. Training R-squared, 1.00. Testing R-squared, 1.00. Processing time, 1.04 seconds. In the context of machine learning, especially when evaluating the performance of a regression model, two important metrics often used are the root mean squared error, RMSE, and the R-squared, R2R2R2, score. Let's break down each of these metrics and interpret the results provided. 1. Root mean squared error, RMSE. Definition: RMSE measures the average magnitude of error between the predicted values by the model and the actual values. It is the square root of the average of squared differences between the predicted and actual values. Mathematically, RMSE is calculated as RMSE equals 1n sigma I equals 1n, y caret I, 2 backslash text RMSE equals backslash sqrt backslash frac 1n backslash sum underscore I equals 1 caret n, y underscore I, backslash hat y underscore I, caret 2 RMSE equals n1 I equals 1 sigma n, y caret I, 2. Where y underscore I is the actual value. Y caret I backslash hat y underscore e caret I is the predicted value. NNN is the number of data points. Interpretation: lower RMSE values indicate that the model's predictions are closer to the actual values, meaning better accuracy. Conversely, higher RMSE values indicate greater error in the model's predictions. 2. R-squared, R2R caret 2 R2. Definition: R-squared is a statistical measure that represents the proportion of the variance for a dependent variable that's explained by an independent variable or variables in a regression model. It gives an idea of how well the independent variables explain the variability of the dependent variable. Mathematically, R2R caret 2 R2 is calculated as R2 equals 1 sigma I equals 1 n, y caret I, 2 sigma I equals 1 n, y,
2r caret 2 equals 1, backslash frac backslash sum underscore I equals 1 caret n, y underscore I, backslash hat y underscore I, caret 2 backslash sum underscore I equals 1 caret n, y underscore I, backslash bar y, caret 2 r2 equals 1 sigma I equals 1 n, y, 2 sigma I equals 1 n, y caret I, 2. Where y underscore I is the actual value. Y caret I backslash hat y underscore e caret I is the predicted value. Y backslash bar y is the mean of the actual values. Interpretation. R2 caret 2 R2 values range from 0 to 1. A value of 1 indicates that the model perfectly explains the variance in the dependent variable, while a value of 0 indicates that the model does not explain any of the variance. An R2 caret 2 R2 value close to 1 suggests that the model fits the data very well. Interpretation of results. 1 average cross-validation RMSE, 7336.86. This value represents the average RMSE obtained during the cross-validation process. Cross-validation involves splitting the data into multiple subsets, folds, training the model on some folds, and testing it on the remaining fold. The RMSE value of 7336.86 indicates the average error across all these folds. Interpretation. While this value might seem large, its interpretation depends on the scale of the data. In this case, it indicates that on average, the model's predictions are off by 7336.86 THB in the cross-validation folds. 2 average cross-validation R-squared, 0.96. This value represents the average R2 caret 2 R2 score obtained during cross-validation. A score of 0.96 means that 96% of the variance in the dependent variable is explained by the model. Interpretation. This high R2 caret 2 R2 value suggests that the model performs very well across different cross-validation folds, indicating that it consistently explains the majority of the variance in the data. 3 Training RMSE, 2488.84. The RMSE value on the training dataset is 2488.84. This is the error when the model is tested on the same data it was trained on. Interpretation. The model has a lower RMSE on the training set compared to the cross-validation RMSE, which is expected since the model is likely to perform better on data it has seen before. The error is quite low, indicating a good fit on the training data. 4 Testing RMSE, 2019.47. The RMSE value on the testing dataset is 2019.47. This is the error when the model is tested on new data it has not seen during training. Interpretation. The testing RMSE is slightly lower than the training RMSE, which suggests that the model generalizes well to new data and has not overfitted the training data. 5 Training R-squared, 1.00. The R2 caret 2 R2 score on the training data is 1.00, which indicates a perfect fit for the training data. Interpretation. The model has perfectly explained the variance in the training data, which is usually an indication of a very powerful model like random forest, which might lead to overfitting if not properly tuned. However, given the low testing RMSE, it seems the model has not overfitted in this case. 6 Testing R-squared, 1.00. The R2 caret 2 R2 score on the testing data is also 1.00. Interpretation. This is an excellent result, indicating that the model has perfectly explained the variance in the testing data. Such a result is rare in practice and suggests that the model has captured the underlying pattern in the data very well. 7 Processing time, 1.04 seconds. This value indicates the total time taken by the model to execute the entire process, including data generation, model training, evaluation, and visualization. Interpretation. A processing time of 1.04 seconds is very efficient for the operations performed, suggesting that the code is well optimized. Conclusion. Your AI/ML model performs exceptionally well, with near-perfect R2 caret 2 R2 scores on both training and testing datasets and relatively low RMSE values. The low processing time indicates that the model is computationally efficient. However, in real-world scenarios, results this perfect might warrant additional scrutiny, such as testing with more diverse data to ensure the model's robustness and to rule out any potential data leakage. The concept is part of microeconomics. The analysis of the heat map and its implications for decision-making falls squarely within the realm of microeconomics. Here's a breakdown of why. Focus on individual units. Microeconomics examines the behavior of individual economic agents, such as firms and consumers. In this case, the analysis focuses on the relationships between specific features, denier, quantity, and unit price, within a particular industry, tire cord and textile. Price and quantity analysis. The heat map directly involves price, unit price, and quantity, which are fundamental concepts in microeconomics. Decision-making at the firm level. The discussion about using the heat map to optimize inventory and inform pricing strategies aligns with the microeconomic perspective of decision-making at the firm level. While macroeconomics deals with the overall economy, microeconomics delves into the intricacies of individual economic units and their interactions. Therefore, the analysis presented in the heat map is a clear example of microeconomic analysis. Exploring microeconomic concepts related to the heat map. 1. Elasticity. Price elasticity of demand. Analyzing the relationship between unit price and quantity can help determine how sensitive demand for the product is to price changes. If the correlation between unit price and quantity is strong and negative, it suggests a relatively elastic demand. Income elasticity of demand. While not explicitly shown in the heat map, understanding how changes in income affect the demand for different denier types could be valuable. This would involve analyzing historical data or conducting market research. 2. Production theory. Production possibility frontier, PPF. While not directly represented in the heat map, the concept of production possibilities can be applied to understand the trade-offs involved in producing different denier types or quantities. If resources are limited, increasing the production of one denier type might necessitate reducing the production of another. 3. Cost analysis. Cost functions. The heat map can provide insights into cost behavior. For instance, if there's a strong positive correlation between quantity and unit price, it might indicate economies of scale, where average cost decreases as production increases. Cost minimization. Understanding the relationships between denier, quantity, and unit price can help identify the optimal production mix to minimize costs. 4. Market structure. Competition. The heat map can indirectly provide clues about market structure. If there are many competitors offering similar products, price competition might be intense, leading to a more elastic demand curve. 5. Pricing strategy. Price discrimination. If different denier types cater to different customer segments, the company might consider price discrimination strategies. Analyzing the price elasticity of demand for each segment can help optimize pricing. Let's delve deeper into production theory. Production theory seems like a promising avenue to explore given the heat map's focus on quantity and potentially related cost implications. Production possibility frontier, PPF, and the heat map. While not explicitly shown on the heat map, the concept of a PPF is inherently linked to the data presented. Imagine a PPF for the production of different denier types. The curve would illustrate the various combinations of denier types that can be produced with the available resources and technology. How can the heat map inform our understanding of the PPF? Resource constraints. The heat map might indirectly indicate resource constraints if there are upper limits to the quantities produced for certain denier types. Technological efficiency. If the heat map shows that production is concentrated in specific areas, example high quantities of denier 1620, it could suggest that the company has optimized its production process for that particular denier. Opportunity cost. By analyzing the correlation between the quantities of different denier types, we can infer the opportunity cost of producing more of one type relative to another. For example, if increasing the production of denier 1620 significantly reduces the production of denier 626, the opportunity cost of producing more denier 1620 is relatively high. ISO quants and production function. While the heat map itself doesn't directly show ISO quants, we can infer their existence based on the data. Isoquants represent different levels of output that can be produced with various combinations of inputs. Potential analysis: if we had additional data on labor, capital, and other inputs, we could potentially estimate production functions and derive isoquants. Input optimization: understanding the shape of the isoquants, example convex or linear, would help determine the optimal input combinations to produce a given output level at the lowest cost. Let's explore returns to scale. Returns to scale refers to how output changes when all inputs are increased proportionally. Types of returns to scale. Increasing returns to scale: output increases proportionally more than the increase in inputs. This often occurs due to specialization, technological advancements, or economies of scale. Constant returns to scale: output increases proportionally to the increase in inputs. This is a neutral situation where there are no significant economies or diseconomies of scale. Decreasing returns to scale: output increases proportionally less than the increase in inputs. This often happens due to managerial inefficiencies or resource constraints. How to determine returns to scale? To determine the type of returns to scale, we can use the following approach. 1. Increase all inputs by a certain percentage, example 10%. 2. Calculate the percentage change in output. 3. Compare the percentage change in output to the percentage change in inputs. If output increases by more than 10%, it's increasing returns to scale. If output increases by exactly 10%, it's constant returns to scale. If output increases by less than 10%, it's decreasing returns to scale. Example. Let's assume that doubling all inputs, labor and capital, results in a tripling of output. This would indicate increasing returns to scale. Implications of returns to scale. Industry structure: industries with increasing returns to scale tend to have fewer, larger firms, oligopolies or monopolies. Cost structure: firms with increasing returns to scale often experience economies of scale, leading to lower average costs. Competitive advantage: understanding returns to scale can help firms identify opportunities for growth and cost reduction. Would you like to explore a hypothetical example with specific numbers or delve into other concepts like the marginal rate of technical substitution or cost curves? Let's explore marginal rate of technical substitution, MRTS. Marginal rate of technical substitution, MRTS, is the rate at which one input can be substituted for another while keeping output constant. It's a crucial concept in understanding the flexibility in production processes. Understanding MRTS. Definition: it's the absolute value of the slope of an isoquant. Interpretation: it tells us how much of one input, example capital, can be reduced for a 1-unit increase in another input, example labor, without changing output. Example. Let's assume we have the following production function: Q equals K caret 0.5 asterisk L caret 0.5, where Q is output, K is capital, and L is labor. To calculate MRTS, we first find the marginal product of capital, MPK, and marginal product of labor, MPL. MPK equals 0.5 asterisk K caret, minus 0.5, asterisk L caret 0.5. MPL equals 0.5 asterisk K caret 0.5 asterisk L caret, minus 0.5. MRTS equals MPL slash MPK equals 0.5 asterisk K caret 0.5 asterisk L caret, minus 0.5, slash 0.5 asterisk K caret, minus 0.5, asterisk L caret 0.5, equals K slash L. This means that the MRTS is equal to the ratio of capital to labor. For instance, if K equals 100 and L equals 50, the MRTS is 2. This implies that we can reduce capital by 2 units for every 1 unit increase in labor while keeping output constant. Diminishing MRTS. Typically, the MRTS diminishes as we substitute one input for another. This is because as we increase one input, example labor, its marginal productivity decreases, while the marginal productivity of the other input, capital, increases. Implications of MRTS. Optimal input combination: Firms aim to produce at a point where the MRTS equals the input price ratio, wage rate divided by rental rate of capital, to minimize costs. ISO cost lines: by combining MRTS with ISO cost lines, lines representing equal total cost, we can determine the optimal input combination. Let's build a hypothetical example. Assumptions. We have data on the production of two denier types, 1620 and 626. The primary inputs are labor and capital. We have information on the quantity produced for each denier type and the corresponding labor and capital inputs. Data table. Denier type quantity, kg, labor, hours, capital, units. 1620 1500 200. 626 800 400 150. Export to sheets. Building the PPF. 1. Identify maximum production points, determine the maximum quantity of each denier type that can be produced with the available resources. 2. Plot the points, plot these maximum production points on a graph with quantity of denier 1620 on the x-axis and quantity of denier 626 on the y-axis. 3. Connect the points, connect these points to form the PPF curve. Incorporating ISO quants. To introduce ISO quants, we would need additional data on different output levels for various combinations of labor and capital. For simplicity, let's assume we have data for two output levels, 800 kilograms and 1200 kilograms. Data table, additional. Output, kg, labor, hours, capital, units. 800 400 150. 800 300 200. 1200 600 250. 1200 500 300. Export to sheets. 1. Plot ISO quants, plot the combinations of labor and capital that produce the same output level on the same graph as the PPF. 2. Analyze efficiency, the optimal production point would be where an ISO quant is tangent to the PPF. This represents the maximum output for a given level of inputs. Incorporating costs. Cost data, we would need information on the cost of labor and capital, wage rates and rental rates. ISO cost lines, plot ISO cost lines, lines representing equal total cost, on the same graph. Cost minimization, the optimal production point occurs where an ISO quant is tangent to the lowest ISO cost line. Challenges and considerations. Data availability, obtaining accurate and comprehensive data on inputs, outputs, and costs can be challenging. Simplifying assumptions, the example assumes a simplified production process with only two inputs and two outputs. Real-world scenarios are often more complex. Dynamic nature, production processes and resource availability can change over time, affecting the shape of the PPF and ISO quants. Proceed with calculations or explore a different aspect of production theory. We could also discuss concepts like returns to scale, marginal rate of technical substitution, or the relationship between cost curves and production functions. Let's analyze the heat map and its significance for DSS. Heat map content, training data set, WIP. The heat map visualizes the correlation matrix of a training data set related to the tire cord and textile industry with a dipping plant. The data is a work in progress, WIP, as of March 31, 2024. Key features. Features, the heat map considers three features, denier, quantity, kg, and unit price, THB. Values, the color intensity represents the correlation coefficient between features. Brighter colors indicate stronger positive or negative correlations. Denier is a unit of linear density that characterizes the fineness of fibers. It seems there are three different denier values in the data set, 1620, 626, and 1616. Quantity, kg, this represents the weight of the material. Unit price, THB, the price per unit of the material in Thai baht. Observations. High correlation, some features exhibit strong correlations, indicated by the intense yellow and purple blocks. For instance, there's a high positive correlation between denier 1620 and quantity, kg. Low correlation, weaker correlations are depicted by lighter shades, suggesting a less pronounced relationship between those features. Missing values, there are some blank cells, possibly representing missing data or features with no correlation. Importance of heat maps for DSS. Heat maps are valuable tools in decision support systems, DSS, for several reasons. 1. Feature analysis, they help understand the relationships between variables in a data set, aiding in feature selection and model building. 2. Data exploration, heat maps offer a visual overview of data distributions and potential patterns, facilitating data exploration and discovery. 3. Outlier detection, unusual values or patterns can be identified through heat maps, enabling outlier detection and data cleaning. 4. Model interpretation, in machine learning, heat maps can help interpret model behavior by visualizing feature importance and interactions. Specific use cases in this context. Identifying key drivers, understanding the correlation between denier, quantity, and unit price can help identify key factors influencing production costs or pricing strategies. Optimizing inventory, analyzing the relationship between quantity and unit price can inform inventory management decisions. Predictive modeling, correlations can be used as input features for predictive models to forecast trends or optimize processes. Limitations. Correlation versus causation, it's crucial to remember that correlation does not imply causation. Further analysis is needed to establish causal relationships. Data quality, the accuracy of the heat map depends on the quality of the underlying data. Outliers or missing values can impact the results. Next steps. To gain deeper insights, it would be beneficial to explore data distributions, visualize the distribution of each feature using histograms or box plots. Calculate correlation coefficients, quantify the strength of relationships using statistical measures. Investigate missing data, understand the reasons for missing values and consider imputation or removal strategies. By carefully analyzing the heat map and considering these additional steps, you can extract valuable insights to support decision-making within the tire cord and textile industry. In microeconomics, heat maps can be a powerful tool for visualizing and analyzing data to gain insights into various economic phenomena. Here's how heat maps are important in microeconomics. 1. Understanding consumer behavior. Consumer preferences, heat maps can show how consumer preferences vary across different products, services, or price points. This helps businesses understand which products are more popular and why. Demand analysis, by visualizing demand patterns across different times or regions, heat maps can reveal where demand is highest and lowest, aiding in targeted marketing and inventory management. 2. Price sensitivity and elasticity. Price elasticity, heat maps can illustrate how changes in price impact demand for different goods. This can help businesses and policymakers understand price sensitivity and make pricing decisions. Competitive analysis, by comparing price sensitivity across different markets, heat maps can show competitive dynamics and how price changes affect market share. 3. Market segmentation. Segment analysis, heat maps can help identify different market segments based on various criteria such as income levels, geographic location, or purchasing behavior. This segmentation allows for more tailored and effective marketing strategies. Behavioral patterns, visualizing patterns in consumer behavior across different segments can provide insights into which segments are more profitable or have higher growth potential. 4. Supply chain management. Inventory optimization, heat maps can be used to visualize inventory levels and turnover rates across different locations or time periods. This helps in optimizing inventory management and reducing holding costs. Supply chain disruptions, by visualizing disruptions or delays in the supply chain, heat maps can help in identifying bottlenecks and taking corrective actions. 5. Economic forecasting. Trend analysis, heat maps can display historical data trends and forecast future economic conditions. This can assist in predicting future demand, supply issues, and economic cycles. Scenario analysis, by visualizing different economic scenarios, heat maps can help in assessing the impact of various factors such as policy changes or market shifts. 6. Resource allocation. Cost analysis. Heat maps can illustrate the distribution of costs across different departments, products, or projects, helping in identifying areas of high expenditure and potential savings. Efficiency evaluation. Visualizing operational efficiency metrics across different units or time periods can reveal which areas are performing well and which need improvement. 7. Policy analysis. Impact assessment. Heat maps can be used to evaluate the impact of economic policies on different sectors or demographic groups. This helps in understanding which policies are most effective and where adjustments might be needed. Economic inequality. By visualizing income distribution or wealth across different regions or groups, heat maps can provide insights into economic inequality and inform policy decisions aimed at reducing disparities. Examples of heat map applications in microeconomics. 1. Retail pricing. A heat map showing sales volume across different store locations can help retailers identify which locations are performing best and optimize pricing strategies accordingly. 2. Consumer spending. Heat maps displaying consumer spending patterns by category and region can help businesses understand which products are in high demand and adjust their marketing strategies. 3. Market research. Analyzing survey data with heat maps can reveal preferences and satisfaction levels among different customer segments, guiding product development and service improvements. Overall, heat maps provide a visual representation of complex data, making it easier to identify patterns, trends, and anomalies. This aids in more informed decision-making, better strategic planning, and effective resource management in microeconomics. Let's analyze the heat map and its significance for DSS. Heat map content, test data, WIP. The heat map visualizes the correlation matrix of a test dataset related to the tire cord and textile industry with a dipping plant. The data is a work in progress, WIP, as of March 31, 2024. Key features. Features. The heat map considers 3 features: denier, quantity, kg, and unit price, THB. Values. The color intensity represents the correlation coefficient between features. Brighter colors indicate stronger positive or negative correlations. Denier. Denier is a unit of linear density that characterizes the fineness of fibers. It seems there are 3 different denier values in the dataset: 840, 1620, and 2748. Quantity, kg. This represents the weight of the material. Unit price, THB. The price per unit of the material in Thai baht. Observations. High correlation. Some features exhibit strong correlations, indicated by the intense yellow and purple blocks. For instance, there's a high positive correlation between denier 840 and quantity, kg. Low correlation. Weaker correlations are depicted by lighter shades, suggesting a less pronounced relationship between those features. Missing values. There are no blank cells in this heat map, indicating complete data. Importance of heat maps for DSS. Heat maps are valuable tools in decision support systems, DSS, for several reasons. 1. Feature analysis. They help understand the relationships between variables in a dataset, aiding in feature selection and model building. 2. Data exploration. Heat maps offer a visual overview of data distributions and potential patterns, facilitating data exploration and discovery. 3. Outlier detection. Unusual values or patterns can be identified through heat maps, enabling outlier detection and data cleaning. 4. Model interpretation. In machine learning, heat maps can help interpret model behavior by visualizing feature importance and interactions. Specific use cases in this context. Identifying key drivers. Understanding the correlation between denier, quantity, and unit price can help identify key factors influencing production costs or pricing strategies. Optimizing inventory. Analyzing the relationship between quantity and unit price can inform inventory management decisions. Predictive modeling. Correlations can be used as input features for predictive models to forecast trends or optimize processes. Limitations. Correlation versus causation. It's crucial to remember that correlation does not imply causation. Further analysis is needed to establish causal relationships. Data quality. The accuracy of the heat map depends on the quality of the underlying data. Outliers or missing values can impact the results. Next steps. To gain deeper insights, it would be beneficial to explore data distributions, visualize the distribution of each feature using histograms or box plots. Calculate correlation coefficients, quantify the strength of relationships using statistical measures. Investigate missing data, understand the reasons for missing values and consider imputation or removal strategies. By carefully analyzing the heat map and considering these additional steps, you can extract valuable insights to support decision-making within the tire cord and textile industry. Feel free to ask if you have any more questions. Key differences from the previous heat map. This heat map has no missing values. The correlation values are slightly different. The overall insights remain largely similar. Heat map content, forecast 2024 and 2025, WIP. The heat map presents a forecast for the tire cord and textile industry with a dipping plan for the years 2024 and 2025. Key features. Features. The heat map considers 4 features: denier, quantity, kg, unit price, THB, and total value, THB. Values. The color intensity represents the correlation coefficient between features. Brighter colors indicate stronger positive or negative correlations. Denier, a unit of linear density that characterizes the fineness of fibers. Quantity, kg, the weight of the material. Unit price, THB, the price per unit of the material in Thai baht. Total value, THB, the overall monetary value of the product. Observations. High correlation, strong positive correlations are observed between denier 1620 and all other features, indicated by intense yellow blocks. Moderate correlations, there are moderate positive correlations between quantity, kg, unit price, THB, and total value, THB, as shown by lighter yellow blocks. No negative correlations, there are no strong negative correlations evident in the heat map. Importance of heat maps for DSS. Heat maps are crucial for decision support systems, DSS, due to their ability to visualize complex relationships, clearly depict the relationships between multiple variables, identify patterns and trends, reveal underlying patterns and trends that might not be apparent in raw data, support decision-making, provide insights for informed decision-making by highlighting key factors and potential correlations. Facilitate data exploration, encourage further investigation into specific areas of interest. Specific use cases for this heat map. Product planning, identify which denier types and quantities are forecasted to have the highest total value, guiding product focus and resource allocation. Pricing strategy, analyze the relationship between unit price and total value to optimize pricing decisions. Supply chain management, understand the correlation between quantity and total value to optimize inventory levels and production planning. Risk assessment, identify potential risks based on unexpected correlations or trends in the forecast data. Limitations. Correlation versus causation, the heat map only shows correlations, not causation. Further analysis is required to determine cause and effect relationships. Forecast accuracy, the accuracy of the forecast will impact the reliability of insights derived from the heat map. Next steps. To gain deeper insights, consider time series analysis, analyze the data over time to identify trends and seasonality. Scenario planning, create different scenarios based on varying assumptions to assess potential outcomes. Sensitivity analysis, evaluate how changes in key variables impact the overall forecast. By combining the heat map analysis with these additional steps, you can make more informed and strategic decisions for the tire cord and textile industry. Let's delve deeper into potential use cases. Given the focus on forecasting, let's explore how we can use the heat map to inform scenario planning and risk assessment. Scenario planning. 1. Identify key drivers. Based on the heat map, we can identify the key drivers of total value, example denier 1620. 2. Create scenarios, develop different scenarios based on varying assumptions about these key drivers. For instance, optimistic scenario, assume higher than expected demand for denier 1620 and increased unit prices. Pessimistic scenario, assume lower than expected demand for denier 1620 and decreased unit prices. Base case scenario, assume the forecast remains as is. 3. Analyze implications, evaluate the impact of each scenario on overall revenue, profitability, and resource allocation. 4. Develop contingency plans, create strategies to address potential challenges or capitalize on opportunities identified in the scenarios. Risk assessment. 1. Identify correlations, analyze the heat map for unexpected or strong correlations that might indicate potential risks. 2. Assess vulnerability, evaluate the company's vulnerability to changes in these correlated factors. 3. Develop mitigation strategies, create plans to reduce the impact of potential risks. Example, if there's a strong correlation between denier 1620 and total value, a significant decline in demand for denier 1620 could pose a significant risk to the company's revenue. Thank you.